for inviting me. So this talk is based mostly on the work of Ruben Feynman, and Ruben is a PhD student in my group, and you should check out some of his papers for more details. If we're to understand the mind in computational terms, we need to understand why people are faster and more flexible learners than the best AI systems. But by faster, I mean that people can often learn a new concept from just a single image. If this is your first time seeing a Segway, you might just need to see that one image in order to be able to recognize another one that looks rather different, maybe has much larger tires. And over on the right, human learning is also more flexible. So by the time you learn to recognize something new, you could also parse it into its most important parts and relations. You could generate a new example with drawing or by some other means, or you could even think up a new concept that, like the one over there on the bottom right, that combines various other types of concepts that you already have. Now, how do people do this? And even for a simpler concept like a handwritten letter from a foreign alphabet, people are also faster and more flexible learners than the best AI systems. Again, can learn from one example and then use that concept, even a simple one, for a variety of different tasks. We introduced this challenge, this Murray Exodus referenced it, called the Omegot Challenge back in 2015. Try to learn a new letter like a person from a single example and then use it in a variety of different ways. So just a quick update on where that challenge is. Well, a few years later, we released a 3-year progress report to try to summarize how current neurally grounded models were doing on this task in terms of matching these human capabilities. So if you look in this chart on the left, there was our fully symbolic probabilistic model, this Bayesian program learning model, which could do a variety of different tasks. And there were a lot of really impressive neural network models that could learn a new character, but they were largely focused on this classification task, which is the first row in the table. And a few models would get to more generative tasks, but they also often struggle with issues, like they would produce too much variation. I have some examples there highlighted in red where the neural net would try to produce another instance of a letter and would go off the manifold and produce something that doesn't look like it, or other types of models would not produce enough variation. So in some neurally grounded models, even on a very simple domain, need more flexible task general representations and need a better grapple with compositional structure in the domain, just as related to what Mohit was saying as well. So I see 3 key principles for making progress here, but also more generally with neurally grounded models. So these are broader principles of human level concept learning in this domain. And if we were to produce a generative framework that can do many tasks, including classification, we want to tightly integrate 3 principles: structure, statistics, and sketches. And this maps fairly well onto neuro-symbolic modeling, which is, of course, the topic of this workshop. So by structure, I mean symbolic structure. And by statistics, I mean neural network style statistical modeling. And for sketches, I mean the fact that people have real but often incomplete knowledge underlying many of their everyday concepts. And I think all 3 of these principles are very important. So our proposal, which is really Ruben Feynman's proposal, is called generative neurosymbolic, or GNS modeling. So here concepts are represented as GNS neurosymbolic programs. The symbolic part of the program, the symbolic routines and control flow, capture real compositional and causal structure in the data generating process. But neural subroutines are also working side by side with the symbolic control flow, and these are useful for modeling non-parametric statistical relationships and filling in holes in structural knowledge. So here's a little GNS program there on the bottom left, which can produce an example of a 3D chair. And how this would work, you run the program, and every time you run it, you get a different exemplar of a chair. And it starts with this blank 3D canvas C. And then there's a loop where it's going to decide, all right, I need a new part. What's the relation between that part and the previous parts in the canvas? And then what does that part look like? And then you're going to update your canvas. And then you're going to decide whether you're done or you're going to keep going. And the key aspect of GNS is that those subroutines are actually controlled by powerful neural networks that are operating in a modular way to try to get the best of both worlds. So the power of neural networks and their statistical abilities, but also the compositionality and the causal capabilities of standard programming. So back to 3 principles. Let's talk about how to integrate them. Historically, structure and statistics have been at odds, but there's been a lot of work on how to integrate them, and I have some examples of papers I like that have taken this approach. And I want to acknowledge this previous work, but also mention how GNS is taking a pretty different path here. So a lot of previous work focused on probabilistic reasoning over structured representations, graph logic programs where probability allows you to select the best structured hypothesis. But then at the end of the day, you're finding that a largely symbolic hypothesis or representation, and the probabilities is helping you get there. And purely symbolic structure can have trouble dealing with handling the richness of raw data, and GNS has hypotheses that are both sub-symbolic and symbolic and provide a framework that can potentially span a rich structural knowledge, domains that have those capabilities, but also domains that have much less structural knowledge. So there's an issue with relying on relatively complete structural descriptions as well, and this relates to that last principle, which is about sketches. So here I'm just going to talk about some psychology for a moment. By sketches, I don't necessarily mean literal human drawn sketches, but I have my cursor over here. Here I'm going to highlight a study that was actually done with sketches. So here, Rebecca Lawson, I'm going to study on what's called the illusion of explanatory depth, asked participants to draw some of the key components of a bicycle. And this is a correct bicycle, but participants had to do this from memory. And they made critical errors. They often didn't know where to attach the pedals, or they put the chain around the wrong part of the bicycle and made these key structural errors. So if you're to represent this as a neuro-symbolic program or a symbolic program, it seems like we're missing a lot of key pieces. Like you might know that there are wheels and those wheels should attach to something, but you might not really know how to generate the frame. There are just going to be key holes, it seems, in human conceptual representation for certain things like connecting the chain and attaching the pedals. So it doesn't seem to be a complete symbolic description all the way down in human conceptual representation. There is definitely key compositional symbolic structure, but there are gaps, and that's also partly what we want to understand here. I'm going to tell you about how the GNS modeling can tackle the omniglot challenge I mentioned. And that challenge involves all four of these tasks: classification, parsing, generating new examples, and generating new concepts, all from just one or a few examples. And you can read more about GNS modeling in the ICLR paper that Ruben wrote in 2021. But here, the GNS model of character concepts works as follows. It's a neuro-symbolic probabilistic program that generates probabilistic programs. So what I'm pointing to over here is the type level program generator, which can generate a new type of character. So I'll tell you how it works. Again, you start with a blank canvas C, you decide to generate a part, you then render that onto the canvas. So you might start with a blank canvas, and then you draw the part, and then you render it back to the canvas. Have a neural net module decide whether you're done or not. And if you're not done, you can generate another part and render that onto the canvas. And then in the context of those first two parts, you generate the third part. When you're done, it outputs another neuro-symbolic probabilistic program, which then can add variation to how different exemplars of that character might look. And over here in the bottom right is showing you inside those modules, those subprograms are handled by neural networks that look at what's been done already and then will decide the location of a part, or maybe actually the form of a part with a little recurrent network. The entire model is fit with maximum likelihood estimation based on a bunch of background drawings of people producing letters. And this has key causal compositional information about characters. And it's a sketch because large parts, I think, are really left to implicit knowledge. And we want our GNS approach here to be able to capture all that. Here's the forward model in action, just to show you what it can do in terms of making online predictions for a real character here. But when there's nothing, the model says, okay, well, I'm definitely not stopping because there's nothing drawn yet. And where's that first part going to be? This is its heat map prediction of where that first part is. The open circle is where the part actually started, the first stroke. And then it can actually predict a time course of where the pen would go in that first letter. And you can see the open circles of where the pen actually went in the next time point. So it can make really interesting, fairly accurate predictions in a lot of cases. And then it's done with that first part. And then it makes a prediction of where the second part's going to start. And it has a strong expectation it's going to begin somewhere along where the previous part was. And then again, you can sort of track its predictions here for how that stroke is going to continue. And then by the time it gets to the third part, it's pretty sure that there's a good chance I'm done. but it can go on making predictions if it decides that it's not. So let's go through the Omniglot tasks. I'm first going to tell you about the generating new concepts task. So this is inventing new letters. But how does GNS do as a generative model? If we look at some quantitative metrics, the GNS model has a better test loss than hierarchical LSTMs and LSTMs, and this is when you're evaluating the loss on the drawing trajectories. If you look at the images themselves, you can do better than various variational autoencoders, non-parametric variational autoencoder models. So these are real samples from the data set, and the GNS samples coming up with new letters look like this. The fully symbolic Bayesian program learning model isn't so good at this task because it doesn't have enough of that important correlational structure that the neural network modules are buying us. And if you want to know if GNS is simply copying characters in the data set, we have a bunch of analyses about this in the paper, but just to show you a flavor, these are the real GNS samples, and then the closest thing in the data set according to nearest neighbors. We've seen a lot of cases that is actually producing something fairly new. So we continue through the tasks in the Omniglot challenge. We can look at one-shot classification. And here is what we found when providing people with a new letter from an alphabet that they're unfamiliar with, and then asking them to find another example of that letter written by somebody else. People are about 95% accurate. And the fully symbolic BPL model is about the same level of accuracy, and GNS can also closely match human level accuracy. How this roughly works, it sees just the raw image, it infers a GNS program for that image, and then it tries to refit that program to potential new examples to see what is the best match. In doing so, it can produce very high accuracy from just a single example. For generating new examples, here the task is that humans and the model will see just one instance of a new letter, and then they'd be asked to produce new exemplars. So one of these grids is 9 different instances of different people producing a novel exemplar of that letter, and the other grid are 9 different samples from the GNS model. You can think of this as like a visual Turing test. Can you tell which is which? I'll give you a moment just to look at these different grids and see if you can guess which one is the machine in each case, whether it's A or B. If you can take a look here and just to yourself, you can try to guess, is grid A the machine or is grid B the machine? Maybe over here is grid A the machine or grid B is the machine. I'll give you another 3 seconds and then I will show you the outcome. So in red is showing the machine generated answers. So we're going to evaluate this a bit more formally and see if the model is actually able to pass this visual Turing test, but it's quite hard to tell. Finally, there's parsing. So you can take instances of human-drawn letters and then try to predict how they were actually produced in terms of that latent causal structure. And we find that the real human parts is here in terms of the underlying parts and the order and direction in which they're drawn. In a lot of cases can be closely matched by the GNS model, which is only on the basis of the image predicting that latent causal structure. Of course, we want the GNS model to be more general than handwritten characters. It can be applied to concepts like vehicles that allow different types of composition. If you think about handwritten letters, the type of composition is actually rather structured and rigid, and that there are some parts that always have to be there in a particular order. But for a concept like vehicles, there's lots of different types of vehicles you can think of that are basically free combinations of various types of parts like motors and fins and wheels and windows and handlebars and all of the different parts that are common in vehicles. So in the real world, parts compose in lots of different ways, not just in the particular way that they do with letters. And here, Yanli Zhao, a PhD student in our group, is aiming to study a much wider range of visual compositions. So her task, which we ran with human participants, looks like this, where participants are shown a couple examples of a new concept like ZUPs. And then they're asked, can you generate another ZUP? So here are 9 different people doing that. And largely participants inferred that these 2 parts need to attach in this way, but it seems like the rotation can be somewhat arbitrary. So in this trial, the ZUPs seem to have this core component, which is 2 green parts put together, and then it can have another part which is attached in some way. And in this trial, the pattern seems to be that it's 2 parts that are identical attached in some way. And again, a lot of participants were able to infer that structure. So can we build a computational model, a GNS model that is also able to make these types of inferences? From just a few examples, figure out what is the type of composition that defines this concept. The GNS can be extended to capture these broad different types of composition. And here, again, we want to use the power of neural networks with the compositional backbone of programming language. We have a neural encoder in this version of the GNS model that will look at the support set of examples of, say, a ZUP, and then produce an embedding vector which will summarize those support set. This then seeds a neuro-symbolic probabilistic program which can generate new examples of that concept. Again, in the same style as before, you're starting with the canvas and then you're generating parts and relations, rendering them and deciding when to stop. And you can see that down here where you produce a part, you render it, produce another part, render it, and so on until the model decides it's done, and that becomes a new exemplar which could then be compared with human generation. The modular structure here with neural net modules allows you to have this type of compositionality where you can come in with an existing concept and ask it to add a new part or ask whether or not it's done. And there's no free control of information like in a standard neural network, but we really are imposing this compositionality, which is this key GNS idea. You can train GNS to model the probability of a new token given a previous token. So over here, this is the key probability that it's trying to maximize during meta learning. And it's going to get a lot of different support sets of a bunch of visual examples that belong to a certain class, and then it's going to try to produce new ones. And the meta training data is going to include real human generations from our behavioral experiment and also samples from a symbolic generative procedure, the one that's responsible for generating all of the stimuli in the first place, and is also used in the Bayesian symbolic model that we compare against. We have some early results and we're still working on this, but just to remind you of the task, participants are shown some examples, or the model shown some examples of ZUPs, and then they're asked to generate another one. On the y-axis here is the frequency of different responses. The x-axis is showing different candidate exemplars that people produced where they had an interface where they could drag and drop parts and rotate them and so on. The blue is showing the human frequency. Orange is the GNS generative frequencies, and green is the purely symbolic Bayesian model. And what you'll notice is that people actually had an interesting tendency to try to complete certain patterns that we were not expecting and is hard to formulate in a purely symbolic model. So if they see 4 different rotations of a part, they quite often like to generate the 4th rotation to show they could do something new that also seemed to belong to the family. And over here, same deal. There's 3 different versions of a rotation, and participants want to generate the 4th one. Over on the rightmost column, there's actually 4 available parts, and participants really like to use that 4th part in some way in order to produce a doubling like the other exemplars. And it's hard to capture this type of sort of additional inductive bias in a fully Bayesian model because it induces dependency between all of the exemplars, which is usually an assumption that almost all Bayesian models make, that the exemplars are generated independently given the hypothesis. But the GNS model, by training on a little bit of human data and some additional augmentation, can easily pick up an additional bias on that for completion, in addition to learning a new concept and making meaningful generalizations from just a few examples. I just wanted to quickly give some shout outs to some of the other neuro-symbolic modeling work we're doing in other domains in the lab and the students that are leading them. I just have a couple examples of this, and then I have my conclusion slide. People can learn by asking questions, while AI systems are quite limited in their abilities to do so. So here, Zion Wang, who is a student in the lab, trained a neuro-symbolic model to look at a board in a battleship-like game and then produce a question that would be useful for discerning where the remaining ships are in the board. These questions were formulated in like a subset of lambda calculus, and so it's a neural network generating these symbolic programs, and it turns out this is a really useful, productive way to try to capture the types of questions that people ask when they're playing this game, and can also make interesting compositional generalizations by the fact that it's using this symbolic language. There's other work by Guy Davidson in the lab that has shown that you can do better in terms of the sample complexity and also the way that deep reinforcement learning models generalize by adding a little bit of symbolic structure on their input representation in terms of a representation of objects and relations between those objects. This is a Coxsci paper from last year. And lastly, Maxwell Nye, who was an intern with me in the lab, showed that you were able to use neuro-symbolic modeling to infer an underlying set of grammatical rules that explain some input-output transformations in like a simple text domain. And the nice thing about using neuro-symbolic reasoning here is that you can use the neural network to produce a bunch of different symbolic grammars that are good hypotheses, but you don't need to rely on the neural network to get it exactly right the first time. And you can then run these grammars, compare them against the data that you have, and filter out the ones that make mistakes. In this way, you can make a much more robust system by having this neural generation and symbolic checking. And this was NeurIP's paper in 2020 that I think is a very nice idea for how to improve robustness in these types of systems. So just to wrap up, I want to remind you of the 3 ingredients we started with: structure, statistics, and sketches. They all seem to be key to human conceptual representation. And neuro-symbolic models in general, but GNS models in particular, are promising means for achieving these different principles. So just to offer a couple of concluding thoughts, GNS is a promising framework for learning rich visual concepts in their raw form and producing human-like behavior across a range of different tasks. GNS provides a means of handling key dichotomies in human conceptual representation: structure versus statistics, explicit versus implicit knowledge, symbolic versus sub-symbolic representations. And I think this approach will prove useful for understanding human conceptual representation and inspire frameworks for machine intelligence that better capture structure, statistics, and prior knowledge, all in a single unified approach. Thank you very much.
All right, thank you very much, Brenden. For I won't get to them all because we're having a short break, but I will ask one, and that is it's from Arthur. Can the program sketches contain errors as well as being incomplete, and what are the implications of that?
Yes, thanks, Arthur. That's a great question. They certainly can contain errors, absolutely. But the hope of the sketches, and that's an idea that we're borrowing from the program synthesis community, and I should have mentioned that during the slides. And part of the purpose there is to remove some potential errors or limit the number of errors you're going to make. And so the key idea is like, if you are uncertain in the full causal symbolic specification of the program, it's okay to leave a gap that you're going to fill in later. So it's a way to hopefully reduce errors, but it is certainly not a guarantee that there are going to be no errors. But it is very much part of the way we represent real world concepts. I think there really are gaps that are filled in with more implicit knowledge that are a lot like that. You ask somebody, like, do you know how a refrigerator works? Usually they'll say, yeah, sure. And then you ask, like, describe it in a lot of detail, and they don't get very far. Like, I only get to, like, they're plugged into the wall and there's something that keeps some motor that keeps it cool, or I don't know. That's about that. There are big gaps, right? And so how do we have these representations that are causal and compositional in some ways, but are left to more implicit knowledge in other ways? I think if we understand that for cognitive modeling, it's going to be of tremendous utility in AI as well.
Great. I think this will provide some good raw material for the panel discussion coming up at 12:10. So again, thank you for your talk.